All right, so we have water enters a direct contact heat exchanger at 400 degrees, 10 bar. So let's go ahead and actually write this stuff out. All right, so we have water coming in to one inlet and pressure is 10 bar. The temperature is 400 degrees coming in at what we're going to call inlet 1. Okay. And then at the other inlet, and we'll put him, say this is number 2. So we also have water coming in at T2, 150 degrees Celsius, E2, 10 bar. And then it exits as a single stream. We're going to call this 3 at with a mass flow rate of E kilograms per second, a pressure of 10 bar, and a temperature of 200 degrees Celsius. And we want to find, I'm just going to put it right here, we want to find the mass flow rate of the water at each of those inlets. So we're looking for m dot 1 and m dot 2, both in kilograms per second. And then we want to find the rate of entropy produced, and they want it in kilowatts per Kelvin. So that means that we're looking for sigma dot. All right, and I'll throw my assumptions over here. So the typical assumptions that I make, steady state, and this is a heat exchanger, it's a direct contact heat exchanger. So if we drew our control volume around this whole thing, there's not, the whole thing is going to be insulated because you only want heat to be exchanged between those streams. So my Q dot's equal to 0, my W dot is equal to 0. And then my changes in potential, changes in kinetic energy, all of those are equal to 0. Okay, so I'm going to start my solution over here just so I have everything kind of in the same place. So, well, we've got a couple of options here. We can do our conservation of mass. See what that gives us. So our conservation of mass, dm dt equals the sum of the m dots coming in minus the sum of the m dots going out. Since it's steady state, you just have the sum of the m dots coming in, which is m dot 1 plus m dot 2 equals the sum of the m dots going out, which is just m dot 3. We also have our conservation of energy. So our conservation of energy, and I'll write out the whole thing, we have dE dt equals Q dot. That's a terrible Q dot, isn't it? Q, it's not much better. Q dot minus W dot plus, I've got the sum of the enthalpy plus kinetic energy plus potential energy all coming in minus the same thing going out. I'll just kind of put a little dot, dot, dot with the understanding that some of these things are going to go away. Steady state, Q dot's equal to 0, W dot's equal to 0, and then the changes in kinetic and potential energy are equal to 0. So all we should have, we've got some of the m dot h's going out is equal to some of the m dot h's going in. There we go. And so if we put those two things together, what we're going to get, we have, I'll say, finding our conservation of mass and energy. So we have m dot 1 h1 plus, and actually, since I'm writing it like this, actually, I've switched it around the way I'm writing. I'm writing the inlets equals the outlets. It doesn't matter, right? But m dot 1 h1 plus m dot 2 h2 is equal to m dot 3 h3. That's just our conservation of energy. And then with our conservation of mass, what we're going to do is we're going to, because we know m dot 3, but we have, two mass flow rates that we don't quite know yet, I'm going to eliminate one of those unknown m dots by saying, okay, well, instead of saying m dot 1, let's say that this is going to be m dot 3 minus dot 2 plus m dot 2 h2 equals m dot 3 h3. All right, and so now I can rearrange this guy in terms of enthalpies and that I know or that I can figure out, and then mass flow rates. So I've got m dot 3 h1 minus m dot 2 h1 plus m dot 2 h2 equals m dot 3 h3. And so now I'm just going to gather like terms. So I think I'll put the m dot 3's on the right hand side. So I've got m dot 3 h3 minus h1, and then on the right hand side I'll have m dot 2 times h2 minus h1. And so now I can solve for m dot 2. So just algebraically solving for it. We'll get those h values in a hot second. And then of course I know that m dot 1, which is the other thing that I need, is just m dot 3 for my conservation of mass up there. M dot 1 is just m dot 3 minus m dot 2. All right, so I'll kind of highlight that's what one answer is going to be, and that's what the other answer is going to be. All right, so let's go see what those, yeah, let's see what our properties are. And I know that I'm going to have to figure out S values as well, so I might as well just go ahead and get those while I'm at it. So all I'm going to do is I'm going to look over here at my state 1, so 10 bar, 400 degrees Celsius. You can look in your saturated tables, see that you're above that critical temperature, and you know that you need to go to your superheated tables to figure out what phase you're in. So let's just see. So I've got 10 bar, 10 bar. There we go. Lost it. There we go. All right. So 10 bar, 400 degrees Celsius. There we go. Any properties we want to know are going to be right there. So I'm just going to pull the enthalpy and the entropy value off because I think that's really all I need there. Okay. So why don't I put that over here? So H1 ends up being 3263.9 kilojoules per kilogram. My S1 in the superheated tables is 7.4651. All right. And then state 2, so we're at 10 bar and 150 degrees Celsius. This guy ends up being compressed. And let's go look and make sure that we understand why it's compressed together. So I'm going to look in table A2, and you'll see why I'm going to A2. Oh, come on, not that much. There we go. So 150. So you can see that we're at 10 bar, which is above the saturation temperature. And so what I'm going to do is, I know it's compressed, so I'm going to use one of those compressed liquid approximations, which says that, well, your H value is approximately H sub F at whatever your temperature is. And your S value, same thing, S sub F at whatever temperature it is. And so we can see that at 150, there we go. So I've got here's my H sub F and my S sub F. There we go. So I'm going to go ahead, so 632.2 and 1.8 and change. Let's go ahead and put that over there. So H1, again, it's compressed, so you're using an H sub F at the temperature. So 632.2 kilojoules per kilogram. And then your S1, I'm sorry, this is H2 and S2. So your S2 is 1.8. 418, and it's going to be kilojoules per kilogram K. And then state two, so we've got a pressure and we've got a temperature. So let's actually go to that, back to our tables here. Organized by temperature. So at 200 degrees, you can see we've got a saturation temperature or saturation pressure of 15.54 bar. We are at 10 bar, which means that it's compressed. So I'm going to do the exact same thing as I did for state 2. I'm going to say, well, it's compressed, and I'm going to pull the H sub F and the S sub F value off using one of those compressed liquid approximations that we use quite a bit in this class. So H3, S3, and let's see, make sure that's right. That seems a bit high to me. Oh, it's superheated. Oh my goodness, my goodness, my goodness. My goodness, I'm sorry. It's 10 bar, 200 degrees Celsius. Oh my goodness. Just kidding. Just kidding. I was so confused. We're at 10 bar. Yes, we're at 10 bar. So 10 bar is less than the saturation pressure, so we're not compressed. We are superheated. Sorry for that momentary like, what? What? All right, so let's go to 10 bar, superheated tables. And 10 bar, oops, let's see, 10 bar and what was it again? 200. Oh, darn it. Just on a roll right now. There we go. It's like, why are those numbers that I have written down not looking at all reasonable? Oh, darn it. There you go. Whew. All right, so there's my S value and my H value. So let's go put that down. H value, 2827.9 kilojoules per kilogram. And my S3 is 6.644 kilojoules per kilogram K. All right, and so I'm going to come down here and just plug things in, and I have all the H values. I've got M.3, all that stuff is given to me, so I end up getting, boy, I could have rounded things off, couldn't I? But I've got 8.28. 8.28, and this is going to be in kilograms per second. And then M.3 is my 50, so 50 minus that 8.28 number is going to be, well, I guess if we round it off, it's going to be 41.72 kilograms per second. All right, so we've went ahead and figured out what the mass flow rate is, but now we need to figure out that sigma dot. And so for this guy, I just need to do my entropy balance. So it's my entropy balance. All right. Let's make this a little bit fatter here, a little bit more forgiving. Okay. All right, so entropy balance for an open system. I've got the change in entropy contained within the system boundary plus the rate of entropy transferred across the system boundary by heat transfer plus the net rate of entropy transferred by mass flow plus the rate of entropy produced. And I can get rid of quite a lot of these things because it's, steady state, no heat transfer. There we go. So I've got sigma dot is equal to, actually, let's not get ahead of ourselves. It's going to be the sum of the m dot s's going out minus the sum of the m dot s's going in. And going in, I have one inlet, or going out, I've got one inlet, I should say, I'm sorry. So m dot 3, S3 minus M dot 2, S2 minus M dot 3, I'm sorry, M dot 1, S1. And at this point, I have everything that I need. So I've already calculated all those M dots and everything. So I'm all good. So 5.526. And the units here are going to be kilowatts per Kelvin. There we go. All right. Hopefully that was helpful. Thank you for watching. Let me know if you have any questions.